everyone. My name is Ali Al Behadili, and I am going to talk about my project, Optimization of Injection Brine Composition and the Impact of Geochemical Reactivity. My supervisors are Professor Eric Mackay and Professor Ken Sorby. Here I'm going to talk about background. First, I start with the scale problem. As we know, water injection used to maintain or to support the reservoir pressure. And the sources of injection water, it's almost seawater or produced water reinjection. And the difference between injection and formation water composition causes the scale problem. And here, the common inorganic scale, there are two type of or two common inorganic scale. First is carbonate scales precipitated due to the change or difference in pressure, temperature, and pH. For example, calcite CO3, and the other type is sulfate scale due to the mixing of incompatible brines. For example, barite PaSO4. Here, this plot or this figure shows the mechanism of the injection water. Here, the injection water is very rich in SO4 and formation water rich in barium. So this is example for sulfate scale, the mixing between incompatible brine. Objective or why? What the objective of my project? Study the major factors effect on scale behavior, such as, for example, temperature, brine composition, CO2 concentration, and geochemical effect. Also discover impact of full sulfate seawater and low sulfate seawater used. For example, study the change or the effect in sulfate scale behavior, for example, barium, gypsum, or anhydride, and what the effect of carbonate mineral reaction, for example, calcite, andite, and dolomite. The reasons are what the reason of this of this study is to maximize oil recovery or to increase oil recovery, also decrease the scale problem and their impact, improve brine injection to minimize cost and footprint. Research question of my project, we can say, when is best time to treat injection brine, for how long, and targeting what composition. This picture shows us, for example, what the example of the scale problem inside the pipe. What the methodology of my work? Methodology based on use the CMG software, CMG GIM numerical simulator, and CMG CMOS optimizer are used to model the effect of geochemical reaction in the reservoir on the scaling risk. My study divided to two parts. Parts number one, geochemical reactions. For example, carbonate and sulfate reaction in situ, impact of availability of CO2, understand to which extent the brine composition may be affected, calculate saturation ratio and rate of deposition for a specific mineral scale. The other part is reservoir behavior. For example, water flooding system change in bubble point pressure and support from solution gas drive, example CO2. Compare single porosity and fracture reservoir. Finally, calculate impact on oil recovery and optimize injection design. Results. The results I'm going to show is based on or depending on the information, the ions concentration in formation and injection water shows here in this table. For example, you can see in this table the concentration of magnesium in formation water is about 70, and in injection water is very high concentration, 1,300 milligram per liter. And barium in formation is about 600 milligram per liter, and for SO4 in formation it is 0, and in injection water 2,700 milligram per liter. Results. I will start with this figure show us the initial or the initial reservoir pressure is very close from the bubble point pressure, as we can see these values. Also, at the beginning, water injection rate is not enough to prevent the pressure drop, as we see here. Here in this period, we can see the pressure drop because the water injection is not enough to support the reservoir pressure. After that, the injection rate, the injection pressure support is enough to raise the reservoir pressure above the bubble point, as we see here. In this figure, in figure number 2, oil Oil flow rate supported by water injection from start to about 2019. The water breakthrough happened at the same time, about 2019, here in blue color. Gas-oil ratio increased significantly at the same time of water breakthrough. After that, we can go to the figure number 3. Here, this figure shows us the CO2 concentration around the producer and injector well. CO2 concentration around the producer well, we can see there is no big change in the CO2 concentration around the producer well. It's only about 0.056 to 0.064. So it is no big change. While around the injector well, we can see the drop in the CO2 concentration due to that because the CO2 partitions from oils around injection well into injection water. So we can see here the drop in CO2 concentration in oil around the injector. Figure number 4 explain for us or show us the temperature behavior around the producer and around the injector. As we see here, the reservoir temperature in my model is 100 and injection temperature is 40 degrees. So in the producer, temperature does not change. In injector, temperature decline from 100 to about 40. The increase, this behavior around the injector will increases the CO2 dissolution in water and dissolution of calcite mineral. About geochemical reaction section results. In figure number 1, we can see here it is very clear there is inverse relationship between calcite and dolomite or huntite because the calcite dissolution drive the dolomite or huntite precipitation. That means will give us a lot of calcium ion free in the system. This increases in calcium ions will help or will support the anhydride precipitation when the system is being hot. First, anhydride because the system is hot. After water injection, after water breakthrough, so the temperature goes down. So after we can see here the gypsum start the precipitation when the system being cold. Here in this plot, in the plot figure 3, we can see that this very drop or very sharp drop in barium concentration at the same time of water breakthrough. In equilibrium decreases in barium concentration is purely due to dilution of formation water by seawater. SO4 breakthrough in equilibrium is later than in case no dolomite due to more SO4 consumption by anhydride precipitation. In no dolomite case, due to no anhydride reaction, SO4 available to react with barium. so you can see it is much earlier from equilibrium. That means in case of equilibrium reaction will indirectly reduce the barite scale risk. In figure number 4, we can show us the PaSO for deposition rate in equilibrium case. In this plot, we can see here the, the barite precipitation occur when saturation ratio is greater than 1 and deposition occur between 2030 to 2034, about 3 years. Maximum amount of PaSO4 is about or around 4 kg per day. Finally, thank you very much for all and for the sponsor. And I will be happy for any question or any query about my project. Please contact me on my email fixed on the first slide. Thank you very much.